Gravity. It's an invisible force that governs the motion of everything in the universe. It's the force that makes things fall. From the apple dropping from a tree to objects in zero gravity, gravity is always at work, but it does so much more. Gravity shapes the cosmos, guiding the dance of planets, stars, and galaxies. It holds planets in orbit around stars, ensuring the stability of solar systems. It causes tides on Earth as the moon's gravity pulls on our oceans, creating the rhythmic rise and fall of sea levels. Gravity is a powerful force in the universe. It can even bend light and warp space-time around massive objects like black holes. Everything in space has gravity. Every planet, moon, and star exerts a gravitational pull. The Earth, the Sun, even you. Every object with mass has its own gravitational field. The bigger something is, the stronger its gravity. That's why massive planets like Jupiter have such a strong gravitational pull. Gravity isn't the same everywhere. It varies depending on the mass and distance of objects. It's stronger closer to an object and weaker farther away. This gradient in gravitational strength is crucial for many cosmic phenomena. This difference in gravity's pull is what causes tides on Earth. The moon's gravity creates bulges in our oceans, leading to high and low tides. This difference in gravity's pull is also the key to understanding something called the Roche limit, which determines how close celestial bodies can get before they are torn apart by tidal forces. Imagine a moon orbiting a planet. This moon, like our own, is held together by its own gravity, a force that keeps its surface intact and its structure stable. The moon has its own gravity, holding it together. This gravity is what keeps the moon from falling apart, maintaining its shape and form as it travels through space. The planet also has gravity, pulling on the moon. This gravitational pull is what keeps the moon in orbit, creating a delicate balance between the two celestial bodies. Now imagine the moon getting closer and closer to the planet. As the distance between them decreases, the gravitational interaction between the two intensifies. What happens? The planet's gravity gets stronger and stronger on the moon. This increasing force starts to have a significant impact on the moon's structure. At a certain distance, the planet's gravity becomes stronger than the moon's own gravity. This critical point is where the moon can no longer hold itself together against the planet's pull. This distance is called the Roche limit. It is the point at which the tidal forces from the planet overcome the gravitational forces holding the moon together. When a moon crosses the Roche limit, things get messy. The structural integrity of the moon is compromised, leading to catastrophic consequences. The planet's gravity rips the moon apart. The intense gravitational forces cause the moon to disintegrate, breaking it into smaller pieces. This is because the planet's gravity pulls harder on the near side of the moon than the far side. This differential force, known as tidal force, stretches the moon until it can no longer hold together. One of the most stunning examples of the Roche limit in action is Saturn's rings. Those beautiful rings are made of ice and rock. Scientists believe these rings were once a moon orbiting Saturn. Over time, this moon drifted too close to Saturn inside its Roche limit. Saturn's gravity then ripped the moon apart. The shattered pieces spread out, forming the rings we see today. Saturn's rings are a reminder of the immense power of gravity and the fascinating phenomena that occur in our universe. Section 4. Unlocking Cosmic Mysteries. Understanding the Roche limit helps us understand more than just Saturn's rings. It helps us understand how planetary rings form around other planets. It helps us study comets that break apart near the Sun. The Roche limit even helps us learn about black holes. Black holes have such strong gravity that their Roche limit can extend very far. By studying these cosmic events, we learn more about how gravity shapes our universe. Section 5. A surprising twist. Prepare to be amazed as we delve into the fascinating world of celestial mechanics and the mysterious Roche limit. Here's something cool about the Roche limit. It's not a fixed line in space. Instead, it's a dynamic boundary that changes based on the properties of the objects involved. It depends on what the objects are made of. The composition of celestial bodies plays a crucial role in determining their Roche limit. A moon made of solid rock has a different Roche limit than a moon made of loose ice and dust. This difference is due to the varying structural integrity and density of the materials. The stronger and denser an object is, the closer it can get to a planet without being torn apart. This is because the gravitational forces exerted by the planet have a harder time overcoming the object's internal cohesion. This means that two moons can be at the same distance from a planet, but one might be ripped apart while the other stays intact. The key factor here is their composition and internal structure. It all depends on their composition and internal strength. Understanding these differences helps scientists predict the behavior of celestial bodies in various gravitational environments, adding another layer of intrigue to our study of the cosmos. Section 6. Keep looking up. The Roche limit is a fascinating concept that reveals the delicate balance between gravity and the structure of celestial objects. It reminds us that even seemingly solid objects in space are vulnerable to the powerful forces that govern the cosmos. So, next time you gaze at the stars, remember the Roche limit and the incredible cosmic dance between gravity and matter. There's always more to learn and explore in the vast expanse of space.